We'll see if that comes through. But at any rate, okay. So what do we want to look at? It's really fundamentals. SI units. So the second slide there goes to some SI units. Length is meters, time is seconds, mass is kilograms, temperature is Kelvin, mole for the amount. So you can ignore those others right now. So where does that bring us to? Just some simple considerations. The first day I said, let's go from known to new. Known to new. So force, and I just want you to think in terms of units. Mass times acceleration. So mass is kilograms times meters per second squared. All right, so force units. This is the units of force. Ignore numbers for right now. So that's the units of force. Work is force times distance. So if we had kilograms per meter, kilograms meters per second squared times meters, work, we get to kilogram meters squared per second squared. I say, what's this all matter? Well, this is basically now getting into joules. Getting into the units for joules. We got kilograms meters squared per second squared. Our book, has a couple of R values. The book has a couple of R values that are in from Gen Chem, and this is one of the shifts we need to make from Gen Chem. You use this, and we got used to this. So pressure, oftentimes we were talking about atmospheres, and now we're shifting on into kilopascals for pressure, and that is coming to, there's a relationship between joules and pascals that kind of flow out of these units. A joule is a Newton meter. I think that responds to a Newton meter. So we got a force times distance. And there's a relationship now between this and this. Newton meter, kilogram per meter squared per second squared. I want to get the R values. We got 8. So we had this in Gen Chem, and we're starting to see this a little bit more here. Okay, so there's a way, if you kind of keep with your SI units, where you can end up with either pascals or bars, something like that, with working off of SI units. Yeah, when I first started looking at this, and I thought, well, why doesn't the author have an R value for Pascal? Yeah, pascals.
Yeah, I thought the same thing.
Yeah. Right away you think, well, wouldn't it be pretty obvious to have one for pascals? And he doesn't, but I think it's such a clear way from the 8.314 joules per mole Kelvin to liter pascals or kilopascals, that it's not that common to use that R value. So these are the two most common R values, and the very first problem I gave you asked you to calculate the pressure in atmospheres and asked you to calculate the pressure in what, pascals? Is that what I, on the homework? I think. Yeah. So you ended up with, you have one with liter bars per mole Kelvin, and then you can convert your bars to pascals or kilopascals. All right, so just kind of follow the units a little bit. And the only way, the reason I'm introducing this, sometimes you can kind of go back to this and say, well, what are the units here for force? It's kilogram meters per second squared. What's the units for work? Kilogram meters squared per second squared. And then how would that relate to joules and kilopascals? In terms of derivatives, the book talks a little bit about, makes a distinction between a slope of a straight line as kind of a different from differentials. But think of this for a second. We've got y equals mx plus b. So y is or f of x, so y, a function of x equals mx plus b. So now take the derivative of y with respect to x for this straight line. And so you got the d of mx plus b dx, and the derivative of b is 0. The derivative of mx with respect to x is m, right? So you can see that in this simple equation, we're not talking about a separate case. We could do the derivative of that with respect to x, and the answer is m. All right, so why am I saying that? So we got a straight line. And basically what we're saying is that if I drew a tangent to this line, what would the derivative of that tangent be? Well, a tangent to this line is going to be on that line. Every tangent to the line is going to be on the line. So d of y over d of x is m at every point along the line. So just kind of going from what you're familiar with to what we're getting into. What we're getting into is, now we're getting into relationships that can be like this, or they can be like this, or whatever, or they can be like this. And so now what we're doing is we're saying, okay, dy over dx is we've got a function now that's a little bit more complicated than this function. And what we're doing with our derivatives is we're saying, okay, what would be the slope of this line that's tangent to that line at that particular point? All right? So that's all we got here, is we've just got a curve, and we've got a little bit more complicated function than this straightforward function. But this is not doesn't need to be thought of as a different class. The delta y over delta x is the same. It's the same along the line everywhere you go. So that's all I'm pointing out there. You got a simple derivative. This dm x has got a power of 1, so we put 1 m to the x and minus 1 is 0, so it's m. Okay, let's take one other example to start getting into derivatives. When we do your homework problem, this next set, 1B, is starting to get into derivatives and partial derivatives. So, but it's working with pressure and volume and temperature. They're kind of a little bit harder to get a hand on. So, let's see, did I skip anything? So what's the equation for the volume of a cylinder?
R squared minus H.
Okay, so we've got a radius of the cylinder here, and we have a height of the cylinder here. So let's do differentiation of this equation right now. What is dV is going to be the partial of V with respect to R, constant H, plus the partial of V with respect to H at constant R. And I guess what we got to do here, we need a dr, right? So we have, this is with respect to constant H. So we got pi H. Those are constants. So it's going to be pi H, and it's going to be 2R. Right? N is 2, so we're going to bring N in front. So going back to my derivatives that I gave you, the derivative of if you have derivative of you got x to the n, right? If you got an x to the n power, then it's n x to the n minus 1. So n is 2, right? You with me? dr plus, now this is all a constant. We're doing it at constant R, so that's a constant. N is 1, n minus 1 is 0, that's just that, simply that. With me? Okay, well, let's
Do we
use
have to
this.
put dr and dh for the chain rule, like even if it's, I
guess if we want the if we want the total derivative for volume, yeah, I would think we still need this, and I'm going to give you an example right now. We're going to use that. All right? So consider that R equals 2 centimeters plus or minus 0.01 centimeters, and H equals 10 centimeters plus or minus 0.01 centimeters. So now here's your dr, and here's your dH. So now you could actually calculate dV by this equation. And go ahead and do that. The first thing you got to do is you got to calculate, let's see. Wait a minute. You got to calculate D. You need to know V. Oh, yeah, okay. You don't need to know dV. This is going to calculate dV. This is going to be the deviation. If R deviated by that much, H deviated by that much, what would be the total deviation in the volume? So from the actual volume, you'll get the volume plus or minus this dV, which will give you the deviation in your volume. All right, so you can calculate dV from this equation right here. Yeah, I guess both of those. If you look at units, we've got centimeters here, and centimeters here, so that's going to be cubic centimeters. And we've got centimeters squared and centimeters here, cubic centimeters. So all of those deviations are going to be in cubic centimeters. I am getting something like, I think you guys have, plus 0.126. I get something like about 1.39 cubic centimeters. You got that, Grant?
I'm off by a factor of 10. So
You're off by a factor of 10.
much higher.
I got that.
What did I do?
Well, Grant, we will all feel much better if we find that you got one. We got one before you did.
It's pretty common.
Sorry about that.
I normally take things when I cook that are wrong.
Well, we all do it. You just don't do it as often as the rest of us. Okay, so all I'm doing here is trying to get something you get your hands around and do some partial derivatives of it and see that it goes somewhere. Okay, Liz, go ahead and figure out what we get here for volume.
Base 21.
125.7.
Okay, you probably used a better value for pi. I had 126, 125, that's
Yeah, 125.7.
125 point what?
0.7.
Okay, so 126 or 125.7. And so now what we got here, this is the volume of the cylinder. This is the accuracy with which we measured it. So these could be off by this amount. So what we're saying is if our numbers deviated by this amount, what would be the deviation in our volume? So what we really have here now, I'm running out of space, but I'll just take it. So we got 126 cubic centimeters, 126 plus or minus 1.4 cubic centimeters. So our deviation, if we rounded that off, our deviation is here in this third, or if you had 125.7, here's where our deviation is. And in Gen Chem, when you learned rules for rounding off numbers, when multiplying and dividing, you take the number with the least number of significant figures, and you report an answer to that number of significant figures. This is really the derivation of that. This is really where that thinking comes from. They do differentials and that sort of thing on it, and say, okay, if that was your accuracy, we deviated by that, how would our answer deviate? It would deviate this way. They're going back to this as proof for those rules. All right, so here we got our volume, and here we have our total differential in the volume given certain deviations in the measurement of it, of the radius and the height. Yeah, and I guess the radius, I don't know, the radius, the DR seems to be having a bigger impact because it's a squared term. It's contributing a lot more. So the accuracy with which you calculate that radius is critical to the overall accuracy of the volume. Yes?
I guess I'm just kind of confused, so from the original derivative sheet, that dr is du dx. So
Yeah, let me see. I don't have mine in front of me.
So it's
Where are you?
so I guess this one here. Where do we get the dr?
Yeah.
Is that? And I thought it was just the derivative of your variable, right?
Falling out, correct answer.
Of what's inside r.
Partial v with respect to r. Yeah, and I think maybe the difference, I'm not sure, but I think the difference is that this is a straight derivative.
You don't have to.
Now we're into a partial.
You don't have to, but it's just
Partial
You have to go to the
derivative.
program point. So
Because I
you already
think
went to it
that's-
later, basically.
Now, so basically, so yeah.
I hear your question. I understand what you're asking me. I can't give you a straightforward answer. I think these are not partial derivatives, these are derivatives.
We know where.
These are straightforward derivatives. And here we're going, we got a full derivative here, but it's the sum of two partial derivatives. I think that's it, okay?
And it's
I think as we get using this a little bit more commonly, we'll get more familiar with it. And certainly the homework is going to have you start wading on into partial derivatives.
Yeah, I have so number 2 and in the next homework, or no, yeah, it says when it's it basically has the same question, but it says when it's increased by 0.5 Kelvin or decrease, and then something else is decreased, the volume is decreased by this amount. So it's not really a plus or minus, it's just it's increased by this much.
Yeah,
do you see what I'm saying? Like how
So
would
this
you?
is gonna be your DT.
Okay. So
and-
you would just plug that into your.
Right.
So that would be the plus or minus, even though they're saying it was increased by this much.
Yeah, Dominic is asking a question about,
Number 2B.
yeah, so without wading into that too deeply, you are going to end up with an expression yeah, so 1A is going to end up
Yep.
with an expression of dP, the full differential, the total differential pressure for the van der Waals equation. And you're going to have expressions with dt and dv in them. Yeah, and so then those in question 2b, that's going to be your dt and your what? Your dv? Is that the volume?
Yeah, DT.
Yeah, and you're going to get the total differential for pressure. Yeah, you will just use those. Those will be
Okay.
plus or
Just plug
minuses.
those in,
Those
yeah.
that if it deviates that much in temperature, and I think you also, since the volume has gone down, you have to put that in there as a negative deviation in volume, and then you can solve the rest of it. I've started, well, I've got most of the answers to all that, but I don't have it all organized. And I didn't do problem 3 yet, because I was really hunting around, or 4, so. Okay. Let's see.
So we should be doing the one or the other. But you're gonna have to take them.
I'll do, apparently you are emailing or communicating with one another, which is great. I just hope everybody has someone they can reach out to and say, you know, it looks to me like the answer to this problem is wrong. Do you think that too? Those kind of things, or whatever. So I hope everybody has a contact outside of class.
You can just make a group chat.
Could we
Add those? Yeah, the add girls to our group chat. After
And
class.
I can't add the other.
the emails you sent, and Liz, you asked me about answers to the other slide. I haven't gotten
That's
to
okay.
calculate those yet. But the emails to me are great, and if you're struggling or have a question, or that was good. I think we solved some problems in between class times, and that's good. I'm trying to think if there's a problem worth dealing with right now here. Well, let's just do one of the homeworks on 1B. Problem 117, I think it's number 5. It's pretty straightforward, but it would be a good extension of what we've done right here. So,
Did you do? I thought they did it with the custody. Did it with custody. I don't have that. Volume's constant. That's it.
yeah, so problem, this is number 5. It's 117. A, B, C, D, E. let's just look at E. So we're saying that we have, and this is pretty straightforward. They're just saying, let's go off of the ideal gas law, and let's take a look at the partial of P with respect to N at constant T and V. So we're taking the partial of the pressure with respect to the number of moles at constant temperature and volume. So to do that, you're going to want to rearrange this as P equals what? nRT over V. So rearrange just the ideal gas law. Here's our new function. So here's our partial. So this is going to be the partial of nRT over V with respect to N. Which is what? This is constant. This is constant. This is constant.
Shows RT.
Yeah. The N is 1. So if we got N to the N power. All right, N equals 1. So you're going to bring that in front of here, and you're going to get N minus 1, which is going to be 0. So this is going to go to 0. No, it's going to go to 1. Excuse me. So that's going to go to 1. And so we just have RT over V. So the partial of P with respect to N at a constant T and V is RT over V. Okay? So really, this problem is probably one of the simpler problems in there. It's just a little bit of practice with partial derivatives.
So then do you have to multiply it by dt? Or no? I guess I'm trying to relate like
Right.
that. I'm just confused about that dr and dh.
Yeah, I think if we were trying to put together this kind of an equation,
Okay.
yes, you'd have to multiply by the,
But if t is just a value,
The
the derivative
dn.
of a value is...
yeah. So yeah, the answer is just, I think this may have the answers at the end of the book. But let's do this one, PV equals nRT again. And this one wants you to take the partial. This is probably the hardest one in the list. Wants you to take the partial of V with respect to P at constant N and T. Similar to what you did here, rearrange this equation as V equals something, and then take the partial of V with respect to P. Oh, I'm sorry. This is P. Just keep in mind that's the same as that. So now your N is -1. So you bring your -1. These are all constants. You bring your -1 in front, you get -1 nRT P -1 -1. So it's negative nRT over P squared. Okay, follow? You follow? Okay, this is just some simple derivatives, but just kind of working it out with the ideal gas law as your relationship. So B, C, and D similarly, just go through there, rearrange the equations, and do that. Now let's see. See if there's anything else to mention. Well, what I want to do Friday is just do that 1A, that part of question 1, so that you're set up to finish it, and then start into chapter 2, and we'll start talking about work and heat. We're going to be coming out of state functions, pressure, volume, temperature, moles, state functions, and we're going to be moving on into a non-exact differential, or these path functions. Work and heat are path-dependent functions, whereas these state functions are path-independent functions. You can't just talk about the initial heat, final heat, and get a difference. They are path-dependent. So we'll start talking, and that puts us pretty much on schedule. I'm looking at the schedule. It indicated we should start chapter 2 on Friday, which we will. We'll still do a little bit in chapter 1. I don't know what else. Like I said, I've got the 1A problem solved. I'll try to, I don't know if I'll have them graded by Friday. Maybe will. And I'm not exactly sure how I'll grade. 100 points. There will be partial credit. I mean, if the answer's wrong, there'll be kind of a standard amount off. And then I'll go looking for why the answer's wrong. And if it's a simple error, you had it all set up correctly but forgot to square something, or had the wrong atomic mass, that'll be a minor thing. If it's wrong because you really were going down the wrong path, then it'll be a little bit more off. All right? And the homework, I will provide some coaching or whatever along the way, or we'll look at things this isn't an exercise in figuring out how smart you are. This is an exercise in working out how you do these problems. Okay, that's how I see the homework. The homework is the road to go down to learn how to solve them and to see what kind of challenges there are to solving them. Then I got 5 of them. And that sort of thing. And then we'll go from there. I told you that you can kind of put together a sheet to bring into the exam of equations. You can kind of start keeping track of that. But what I will provide, don't feel like you have to fill that sheet with constants or values of R and things like that, or van der Waals values. If there are constants or things of that nature, I'll probably end up creating a sheet and adding to it each exam with the reference information you have to have. So you kind of think about what equations, what differentials I want to have on that sheet, or whatever you want to have on that sheet as reference for you, and I'll make sure you have the constants and values for R and conversions for pressure, et cetera, like that. I will have a standard handout for that. All right? Good. So, yeah, all this was just kind of starting dipping our toes into the calculus side of this. Great. I'll see you Friday.
Thank you.
Short week.
And will you send out the stuff before Friday, or are you checking it on Friday? The answers to A1? Or?
Yeah, I'll check it on Friday.
Check, okay.
I may get the answers to 1B out there. I'll accept that 1A. Some of these really complicated answers, I don't know when I'll get those out.
Okay.
The numerical answers for some of the problems, I'll try to get those out there pretty soon.
I was wondering, could I shave my horn? I need to box something because you had to hit the one problem in bars, so I converted it into bars, and then it's switched out in kilopascals, so I didn't box my kilopascals. So it's kind of hidden on the fifth one. It's just
Yeah, I solved it in bars and then just back to
it's right here.
Thank you.
Oh, let's get your
Thank you.
phone.
Yeah.
Oh, yeah, I got it.
Oh, you got him?
Yeah,
Okay,
I'm
cool.
gonna send it right now.
Yeah. I'll try to look at that.
Yeah, let me know. Thank you.
Yep, see you later.
See you later. See ya.
Thank you.
Yeah, Grant, see you.
Wait, Grant, what class do you have next?
Heat master.
Oh, that's yeah. So you're
I practice in the building.
really? That's weird. Thank you.
Yeah, see you, Ryan. What's wrong with that?